Hey, what's up? It's Jake from Nimbus DevOps, and we're going to be moving on to generator expressions. This other technique is basically a way to generate values one at a time. It's exactly the same as list comprehension, except instead of wrapping comprehension with square brackets, we're going to wrap it with round brackets, and this is called a generator expression. So in general, generator expressions behave like equivalent list comprehensions, but there's one very important thing to remember, and that's that generators allow for one iteration only, and then they'll be exhausted. So let's take a look at an example. I'm going to go ahead and open up an interactive shell, and I'm just going to say cubes equal, and then I'm going to go k cubed for k in range, and we'll just say 10. And this is just a regular list, right? And if I call cubes, I can see the cubes 1 through 9, essentially. And if I look at the type for cubes, cubes, it's the class list. So now if I make another one and I say cubes gen, and I assign in these round brackets, parentheses, right? K cubed for k in range 10, and this is created as a generator, and then I call cubes gen, you can see the generator object has an expression at some memory index, right? And we can check the type cubes gen and see that it is a class generator. And if I pass list type and then cubes gen, I get the actual values, which will exhaust the generator. But if I do if I do this again, it produces an empty list, and that's because there's nothing more to give. So look at the line where the generator expression is created and assigned the name, and you can see the generator object. In order to see the elements, we can use a for loop, which is a manual set of calls to next, or simply feed it like I did to the list constructor, which is what you see here, list cubes gen, right there. But notice how once the generator's been exhausted, there's no way to recover the same elements from it again. You have to actually recreate it if you want to use it from scratch again. So I'll give you another example where we can reproduce a map and filter using a generator expression, and you can see kind of how this works. So I'm going to define a function adder square or times n, and I'm just going to return the sum of n. That's all I'm going to do. And then I'm going to create a variable s1 and say sum map adder range 100 and then range 1 through 101. And then I'll make an s2, which is sum adder times n for n in, and I will zip the range 100 and range 1 through 101, like that. Okay. So S1 and S2 are exactly the same. They're the sum of the adder 0 to 1, 1 to 2, 2 to 3, and so on, which translates to the sum 1, 3, 5, etc. The syntax is different, and though you find a generator expression to be much more readable, but for the filter now, we look at, if I did like a cubes equals, and then in a list, x cubed for x in range 10, like that, get out of your way so you can see it. I could also do like, well, give me the odd cubes 1 equals, and then here's the filter, and then I'll just make a lambda cube that says, excuse me, cube mod 2 cubes, something like that. And then I spelled this wrong, that's why it's messed up. There. I could make an odd cubes 2, and with a generator, say cube for cube in cubes if cube mod 2. which is a lot of use of the word cubes or cube, but I think you get the idea. There we go. So in this example, odd cubes 1 and odd cubes 2 are the same. They generate a sequence of odd cubes, but we prefer the generator syntax, this one here. Cube for cubing cubes if cube mod 2. This should be evident when things get a little bit more complicated. So if I take a more complicated approach and I said something like capital N equals 20, and then cubes 1 is a map, and in that map I have a lambda n for n and n cubed, comma, I want to filter with another lambda n mod 3 where it doesn't equal 0, or n mod 5 doesn't equal 0, comma, range, whatever capital N is, big N. Lambda, let me make sure this is fixed up. Let's see, I got my map, got this guy with a comma, filter, lambda, n colon, n mod 3 equals 0, or n mod 5 equals 0. There we go. It's a typo. And then I could make a cubes 2 and show you the other way. So cubes 2 equals, and then let's use the generator version. I can say n comma n cubed for n in range big N if n mod 3 equals 0 equals 0, or n mod 5 equals 0, and close it. Yeah, I guess I could close it like that. However you want to do it, you can do it like this. So this code creates two generators, cubes 1 and cubes 2. They're exactly the same and return two tuples, n and cubed, when n is a multiple of 3 or 5. If you print the list cubes 1, you'll get these sets. So like let's say I did a print cubes 1. Okay. Let's exit out of here, clear my screen, and do Python generator expressions. And you get this object at a map area, right? If I did, let's print the lists. And you see I've got these tuples, right? N and n cubed, n and n cubed, n and n cubed, and so on and so on and so on. So the generator expression reads much better. This, I think, you would rather read this than a lambda with a filter with another lambda. So it's just a little bit, I think the generator is a little bit easier to read. It's debatable when things are simple, but as you can see, like if I just make a little bit more complicated, when you start nesting functions, the generator syntax is much, much easier to read. So it's shorter, simpler, more elegant, more Pythonic. So what's the difference between let's do another example. What is the difference between these lines of code? If I did s1 equals sum, and then inside here a list n squared for n in range 10 to the 6th, and then I made an s2 for sum, sum, and then parenthesis n squared for n in range 10 to the 6th, like that. Or a third one that was the sum n squared for n in range 10 to the 6th. They look similar, right? So strictly speaking, they produce the same result. The expressions to get S2 and S3 are exactly the same because the brackets in S2 are redundant, right? They're both generator expressions inside sum function. The expression to get S1 is different though. Inside sum, you'll find list comprehension, right? And this means that in order to calculate S1, the sum function has to call next on a list of 1 million times, 10 to the sixth. So you're losing a lot of time and you're losing a lot of memory. So before sum can start calling on next on that list, the list needs to have to be created, which is a waste of time and space. It's much better for sum to call next on a simple generator expression, and there's no need to have all of the numbers from range 10 to the sixth power or 1 million stored in a list. So you can watch for extra parentheses when you write your expressions. Sometimes it's easy to skip over these details that make your code very different. If you don't believe me, check this version out. So if we said s equals sum and then list n squared for n in range 10 to the ninth, okay, this is going to get killed, right? But if you did the version, and if I printed s, if I said print s, and let me just get rid of all of this code here. We don't need it anymore. If I said print s, let's see what happens. It's just going to sit there and sit there and sit there for a very long time. In the first line, and I've got 64 gigs of RAM, it may finish, it may not finish. Eventually, it'll just get killed. But on the other hand, if you were to rewrite this without list comprehension, let's see what happens. So I'm going to Control C keyboard interrupt, kill that guy. We're going to comment this out, and I'm going to make another S. And I'm just going to say S is sum, and no list comprehension. We're going to use generator, n squared for n in range 10 to the ninth, like this. And if we print this, let's see what happens. Now, remember, it's going through a million values, but you're eventually, if you sit here long enough, it's going to process and it will actually not get killed. So the difference between the two lines is that the first one, a list with the squares of the first billion numbers, must be made before being able to sum them or add them up. And that's a huge list, right? You're going to run out of memory, more than likely. So Python will kill the process for you and just say killed. But if you remove the square brackets, you no longer have a list. The sum function receives 0, 1, 4, 9, etc. until the last one and sums them up, and you won't have a problem. Now you're still doing a billion numbers, so this is going to take forever. So that's just something you want to keep in mind. So if you have any other questions, let me know. But if not, that is an overview on generator expressions. And if you, yeah, just leave me a message in the comments or whatever. And we're always used to doing list comprehension, and list comprehension is great. But just remember that once you start making things more complicated and numbers get larger, list comprehension can waste a lot of time and a lot of space. So just keep that in mind, and I'll see you in the next one.